on, we will consider this problem. We have a polynomial with real coefficients. If there is a constant c such that p of x plus c times p prime of x is greater or equal than 0 for all reals, then we should have p of x greater or equal than 0 for all reals. All right, so here is the problem again. So the first observation that we make is that as x goes to plus or minus infinity, we know that any polynomial as x goes to plus or minus infinity will either go to infinity or minus infinity, right? And what determines if p of x goes to plus infinity or minus infinity is really this leading term right here. So for example, if an is positive as x goes to infinity, this will go to infinity faster than the rest, and therefore p of x will go to plus infinity. If an is negative, as x goes to plus infinity, the polynomial will go to minus infinity, and so on. Right? So it's really the leading term of the polynomial that determines the sign of the values of px whenever x goes to plus or minus infinity. So we want to take the limit as x goes to plus or minus infinity of px plus c times p prime of x. And we know that this is either plus infinity or minus infinity. However, since the polynomial px plus c p prime x is always greater or equal than 0, then as x goes to plus or minus infinity, this polynomial has to go to infinity, once again because it's greater or equal than 0. Right? But it's really the leading term of this px plus c times p prime x that will determine this infinity, right? But what is the leading term? The leading term is actually the leading term of px, because when we take the derivative, the degree of p prime will be 1 less than the degree of px. So therefore, the leading term of this whole expression, px plus c times p prime x, will be just the leading term of px. Right? So therefore, if this goes to infinity, right? So if this goes to infinity, this necessarily will force that limit as x goes to infinity plus or minus infinity px to go to infinity. Another way to see that is if x goes to plus or minus infinity of this polynomial, which has the same leading coefficient as px, if it goes to infinity, then an has to be positive and the degree here has to be even. So that's the only way this can happen, and the same conditions imply that limit as x goes to plus or minus infinity, px is equal to infinity. This in particular means that there is an interval AB outside of which we have px strictly greater than 0. And once again, the reason is because as x goes to either plus or minus infinity, our polynomial will go to infinity. So therefore, outside of a given outside of an interval, of some interval, p of x will be strictly greater than 0. Now remember that our goal is to prove that p of x is greater or equal than 0 for all x. So up to here, we actually proved that it's strictly greater than 0 outside of some interval AB. All right, so now we assume on the contrary that p of x is not greater or equal than 0 for all reals. Then there has to be a point in this interval such that the value at that point is strictly less than 0. On the other hand, our polynomial has to have a local minimum. In fact, it has to have a global minimum, right? It has to have a global minimum because as x goes to plus infinity or minus infinity, the polynomial itself goes to infinity. So therefore, there has to be a point which is a minimum point for the polynomial. All right, so the polynomial should have a minimum value at some point. But at the minimum value, we should have p of x0 is less than 0. The reason is because, again, there is a point where the polynomial, according to our assumption, there is a point where the value is less than 0. So therefore, at the global minimum, p of x0 has to be less than 0. So p of x0 is less than 0. And since x0 is a point where the global minimum is achieved, the derivative has to be 0 at that point, because it's a critical point. But when we plug in x here, when we plug in x0 for x here, p of x0 will be less than 0, p prime of x0 will be equal to 0. So therefore, the existence of a point where p of c is less than 0 will necessarily imply that this polynomial has a negative value at x0. But that contradicts to the original assumption that p of x plus c times p prime of x is greater or equal than 0. So the conclusion is that there cannot exist a point c such that p of c is less than 0. So therefore, p is greater or equal than 0 for all x in R, in the real number system. Right? So p of x is greater or equal than 0 for all x in R, and that concludes the solution.